So, hello everyone. I hope you can hear me. And let's just start with this new appointment of the Joint Astrophysics Colloquium. Today, I'm glad to introduce the Professor Jürgen Blum, that is the leader of the planetary formation and small bodies of the solar system of the Institute for Geophysics and Extraterrestrial Physics of the Technische Universität in Braunschweig. Professor Blum and his co-authors have published almost 250 revealed papers, and his career has covered many topics of high interest spanning from experiment of dust aggregation in low gravity environments, regolith formation, thermal, optical, and mechanical properties of regolith, as well as studying density and porosity of primitive bodies in the solar system, collision among ring particles and structure formation in Saturn's rings, and cometary physics. Professor Blum has successfully applied these studies to the formation of planetary systems and in particular to the initial phases of dust growth and dust collisional evolution in young planetary systems, to the properties of protoplanetary dust aggregates and of the planetesimal and cometesimals. So I will leave the floor to Professor Blum, that will speak about comets as clues to the formation and evolution of planetesimal.
Thank you very much for the kind introduction and the possibility to talk with you about whether comets can tell us anything about the formation of planets. And I hope I can convince you that they can do, but we're still not capable of deciphering everything they might be able to tell us. But let's start at the beginning. I'll show you at the very beginning our latest cartoon of what we think the formation and evolution of small bodies in the solar system could look like. On the horizontal, you see a rough time schedule. So starting very early in the protoplanetary disk, t = 0 is difficult to define, but let's just assume it's the time when the so-called calcium aluminum rich inclusions were formed in the solar nebula. So that's t = 0. Within a very short time scale, this first stage happens. And then within a few million years, the protoplanetary disk exists. At that time, the gas is being dissipated by the young star. And thereafter, the so-called debris disk phase starts, which lasts until today. And I will be talking about all those stages that at least we need to take into account to understand the formation and evolution of small bodies in the contemporary planetary system. But I'll go step by step, so don't worry. So I'll start with the first stages from dust that's readily observed in protoplanetary disk by astronomical observations, both in the visible light as well as with, for instance, ALMA at very long wavelengths. That evolution into bodies called planetesimals. And planetesimals, it was already mentioned in the title, is an artificial word consisting of planet and infinitesimal. So that means a very, very small planet. And we're typically speaking of sizes of a few kilometers if we're talking about planetesimals. So let's start with the first step, from dust grains to pebbles. And as my background is experimental astrophysics or laboratory astrophysics, I'll show you one of our many, many microgravity experiments that was performed in that case in the drop tower in Bremen some years ago, almost a decade ago now, in which we dispersed dust aggregates. And on the bottom right plot, you are seeing a typical dust aggregate, so roughly 100 microns in size, consisting of dust grains that are typically 1 micron in size. And in this case, it was silica and 1.5 microns or 1 micron silica grains, all the same size, all spherical, so that we can compare with theoretical calculations. If I start the movie again, left and right is the same from 2 different viewing angles. You see, we start with relatively small agglomerates, and by mutual collisions, which are happening at a few centimeters per second speed in a vacuum environment, the aggregates come together, stick together, and form extremely fluffy, up to 1 centimeter sized aggregates, and aggregates of aggregates within the 4.5 seconds that the drop tower allowed us to do experiments with. So that's one of the basic experiments that we performed, and we performed literally dozens of different kinds of experiments. And after very, very many of those, in 2010, we came up with our first dust aggregate collision model, who's one of the latest versions you're seeing from 2016. Stefan Koter's PhD thesis is plotted here on the right. What you're seeing is 4 panels. The top left is for typically 1 micron silica grains at 1 AU in the protoplanetary disk. The top right is for 0.1 micron silica at 1 AU, and the 2 bottom ones are for water ice grains, typically 1 micron at 3 AU and 10 AU. And the green color shows you in this size plot where we expect collisions to result in growth, in sticking. And the reddish colors show you where we don't expect that. Yellow is the transition, the bouncing, and red means even negative growth, so fragmentation or erosion, or what you call it. And a potential way to planetesimals, which are in the size on the right or to the top, has to go through green. So you see here's a lot of green for water ice, and there's very, very little green for micron-sized silica. There's a little bit more green for 0.1 micron silica. So one might think that this might be a path to planetesimals. However, the erosion barrier, this little orange thing here, is against it. And we have run a simulation based on the experiments that show that this erosion barrier is indeed exactly here. And the simulation was run by one of my postdocs, Rainer Schräbler. We published it in 2018. And we set in this numerical simulation, all the collisions may result in sticking, except for this little strip here. And even though most of the chart was then green, or almost all of the chart was green, this little red-orange strip did not allow any particle to grow beyond a size of 10 centimeters. So this is why we define barriers, and the erosion barrier is one of them. There's a bouncing barrier, there's a fragmentation barrier, many, many, many. And in the course of the decades, we've been working on this problem. We could show that the barriers depend on the material and on where you are in the protoplanetary disk. So close to the star, in this case, it's 1 AU. Back in 2010, Andras Schomm and us showed that the size, or actually it's the mass of the biggest aggregate you can grow, is on the order of 1 gram. So 1 gram is 1 centimeter. So centimeter-sized bodies that in the course of that we termed pebbles, because they have typically the size of an earthly pebble. A few years later, Sebastian Lorig, another PhD student, ran simulations with icy or ice-rich dust aggregates, and he found out that the dependency on the heliocentric distance, in this case between 5 AU and 50 AU, is very, very strong. So whereas in the innermost regions of the protoplanetary disk, the masses can indeed grow up to 1 gram or a fraction of a gram. In the outer disk, it's merely a milligram or so. So the sizes there that can be achieved by direct collisional sticking are only like 1 millimeter or so. But we call, regardless of the size, anything that has the size of a millimeter or a centimeter or maybe a decimeter, we call a pebble. And the question is, how do we go from here? So we do have pebbles, but we want to end up at least with kilometer-sized planetesimals, which then are big enough, massive enough to attract more stuff, more dusty stuff, or each other in mutual collisions and grow to planetary sizes. And it seemed hopeless before some people discovered a hydrodynamical instability, which is now called the streaming instability, and other people, other group, discovered that a follow-up on that is a gravitational collapse. So I'll show you how this works. I show you a numerical simulation by Jakob Simon. He's one of the main players in the field, but also people in Lund and Heidelberg and elsewhere do run simulations. So what's happening? We're looking in a hydrodynamic simulation perpendicularly down on a protoplanetary disk, and we are co-rotating. So you see the inner part rotating a little bit faster because it's Keplerian, and the outer part slower, and the co-rotation radius is somewhere here. So we are seeing a little slice of protoplanetary disk, and due to this differential rotation and due to the partial decoupling of the dust, the pebbles sizes are sufficient decoupling of the pebbles from the gas motion, the pebbles may concentrate locally. And the color scheme shows you in logarithmic units how much the concentration can be. I still continue a little bit of running these things. And you see here pop out enhancements of up to a factor of 1,000 in concentration. And this is completely without gravity. This is a pure hydrodynamic effect in a Keplerian sheared disk. And if you switch on gravity, you can see that it even goes faster. Within almost no time, a few orbits are sufficient. So it's really rapid. You form typically objects that we would call planetesimals and that are of typically 100 kilometers in size. Out of centimeter-sized or even millimeter-sized pebbles. And these bright things here in these simulations are those pebble piles, 100 kilometer sized objects consisting of pebbles. So the end effect after the streaming instability that gives you an over enhancement of material in the dusty form over the gas, and after the gravitational collapse sets in, is a collapse of everything, of all the material in the environment to form a planetesimal, or here called cometesimal, which looks like that. So it has the size of typically 100 kilometers, can be smaller and must be smaller if we want to talk about comets, which basically consists of these centimeter-sized pebbles and some material in between. So that's the idea. After we have the planetesimals, we have to investigate whether the planetesimals survive for the next 4.5 billion years or what may happen. And the first thing that happens even during the collapse or immediately after the collapse is a mechanical stress occurs. So if we have a planetesimal, and the planetesimal is 100 kilometers in size, there is a lithostatic pressure inside which might or might not destroy the pebbles. So qualitatively spoken, large planetesimals will destroy their pebbles, whereas small planetesimals won't destroy the pebbles. And the same is true for the infall of the pebbles. If they fall into a very large planetesimal, they will be destroyed already at the impact or even during the collapse phase. And for a small planetesimal, that might not happen. So we went into the laboratory, produced some pebble piles here. So you are seeing here millimeter-sized pebbles and a few centimeter-sized cylinder. And we exerted compression, pressure, and measured the filling factor, so the density basically of that pebble pile. And you see a relatively Lin-log relation, so pressure is in log units, so a logarithmic increase in the volume filling factor or density as the pressure increases. And we can compare the artificial pressures we apply in the lab with a real lithostatic pressure, which is 35 Pascal per kilometer radius, but the radius goes squared into the whole calculation. So at the end, if you do the math, we end up at large planetesimals destroy the pebbles because the filling factor goes to unity, so the pebbles are gone. Whereas small planetesimals, in small planetesimals, the pebbles completely survive. Okay, when this has happened, so we're now picking out a small planetesimal that still has all the pebbles intact. The next thing that may happen is the planetesimal may heat up because it may contain short-lived radionuclei, SLN, short-lived nuclei that may decay by radioactive processes. And the point is that a planetesimal that is made up of pebbles has a completely different thermal conductivity and thus a reaction to a heat released in the center of the planetesimal as would be the case for a planetesimal without pebbles. So we take this structure again into account, and now we calculate it and also measured in the laboratory and completely confirmed the thermal conductivity inside such a body, and it turns out it's heavily temperature dependent. If the temperature is low and radiative energy transfer is completely unimportant, then the heat can only be transmitted through the contacts between the pebbles. And you can imagine this contact area is very, very small. So we have conductivities in watt per meter and Kelvin on the order of less than 10 to the minus 3, which is a factor of 1,000 or even 10,000 less than for normal ordinary materials. And that means at low temperatures, the heat conductivity is basically zero. All the heat that is generated by radioactive decay in the center will remain there and heat the center until the temperature rises, and this is the case for 5 millimeter radius pebbles, above a certain limit, a few hundred Kelvin, and then due to radiative heat transfer, the conductivity increases, and then the cooling sets in. So we took into account all kinds of short-lived, or actually aluminum-26 and iron-60 mostly, and some long-lived radioactive nuclei, and calculated what a planetesimal that is made up of pebbles with all different radii on the vertical here, and formation times after CAI, the calcium aluminum rich inclusions, how much they heated. And the formation time is crucial because if the planetesimals are formed early, then they contain much more of the short-lived radionuclei as compared to when they form later. And one example of what's happening inside is the abundance of water in grams per cubic centimeter, initially 0.1 throughout the whole planetesimal. After 4.6 giga years for a planetesimal with 10 kilometers radio and 5 mega years formation time. So we're here, this planetesimal. Throughout the most of the volume, the abundance of the water ice has been reduced to about half, and a very, very narrow thin shell of highly enriched water ice has formed. So water may be extremely volatile in these planetesimals early on already. And the charts here, the pie charts you are seeing here, gives you temperatures. So the black ones is even the super volatiles will remain where they are. So only for small, very small planetesimals, and for those formed very late with fewer radioactive nuclei, all those super volatiles will be retained. Whereas for the early formed large planetesimals, even water can get into the liquid state, reaching temperatures above 273 K and pressures above 600 Pascal. And we're not the only ones who've done those calculations. So that was the work by Uri Malamud and us. Björn Davidsson last year has published very similar things. So he has looked into where is the CO, where's the CO2, and where's the amorphous, what's the amorphous to crystalline water. And he also finds, as a function of depth here for 35 kilometer radius, a blow up of the uppermost 5 kilometers or uppermost 200 meters. He finds different shells with different abundances of these volatile elements. So in essence, that means that small planetesimals, where the amount of radioactive material is relatively small, all of those that formed so late that the amount of radioactive material is also small, remain pristine in their abundances of volatiles, whereas larger planetesimals, or those that have a lot of radioactive material, may differentiate with a depleted, ice-depleted core, ice-enriched shells, different shells for different ices, and a pristine mantle if the environmental temperature is low enough, or this white shell might even reach to the surface, of course, if the temperature is high enough. So that means we have a thermal evolution that ends up already after about 10 megayears, when all the short-lived radionuclei have been decayed, leaves us with two different types of planetesimals, namely type A, undifferentiated, and type B, differentiated for the small ones. The large ones have destroyed the pebbles. The behavior will be different. However, that's not all. For the remainder of the 4.5 billion years until today, there's long-lived radioactive heating, which is not as important as the short-lived nuclei. And there are collisions. And I'll be briefly talking about the collisions now. Again, you're seeing the pebble pile in the lab. And here we have a movie from our laboratory tower in vacuum again. We collided 2 of such pebble piles, in this case at about 10, 11 meters per second collision speed. Each one is a cylinder, and they're crisscrossed so that they match the collisions between spheres. Each one is about 2 centimeters in size. The pebbles are 1 millimeter in size. They consist of SiO2 on the micron scale with the particles. In this case, we pre-compacted the 2 pebble piles to 50 kilopascal. We did different pre-compaction to mimic bodies with different radii. And what you're seeing here is a so-called catastrophic collision. So catastrophic has 2 meanings. First of all, the biggest remnant after the collision is certainly less than half the mass of the original ones. That's one definition. And the other definition is we're still having the pebbles intact. What you're seeing here is individual pebbles flying away. They were not destroyed. And we do distinguish between 3 types of collisional outcomes. So you saw the catastrophic ones, where the pebbles survive, where the bulk morphology is completely destroyed, but where the ices also survive because the impact energy is not sufficient to heat the bodies. There might also be subcatastrophic collisions, so at smaller speeds, where everything survives. So the pebbles survive, the bulk morphology survives. You maybe make a little crater, a little bit of erosion, but nothing else. The ices already also survive. And on the other side, we have the super catastrophic collisions or high speed impacts or impacts between bodies of very similar size at high speeds, where even the pebbles are destroyed, where the ices completely sublimate, and where nothing of the bulk morphology is being destroyed. So the question is, what is the maximum we can allow? So it must be clear that no single body in the late phase of the protoplanetary disk and throughout the debris disk phase can ever escape any collision. So there's no body that has done undergone zero collisions, but we are now seeking for collisions that are relatively harmless. So the collision frequency should be relatively small. That sorts out where in the disk and at which sizes we should look at. The collision speeds should not be too high, and the mass of the collision partner should also not be too high. So if we take everything together, the lithostatic compression, the thermal metamorphosis, and the 3 types of collisions, all 3 end up in loss of memory after 4.5 years to what happened in the protoplanetary disk phase. So we better want no loss of memory. So we do not want large planetesimals to be compressed lithostatically. We better do not want a real good differentiation into volatiles and refractories. And we also don't want the ices to be completely destroyed and the morphology and the pebbles to be destroyed. So we're looking for bodies that do not fulfill the super catastrophic high-speed impact and even pre-pebble compression stage, but we're looking for the other combinations. So in the subcatastrophic collision case, we'll find the original composition and the original makeup. We may find the differentiation with the original makeup. So if the collisions weren't important, but the heating was. Or we do find the opposite. Collisions were important. We are finding pebble piles, but still very homogeneous. Or we might find pebble piles and heterogeneous, and of course the extreme case of super catastrophic collisions. Now we turn to the comets. In search for completely unaltered or relatively unaltered contemporary planetesimals in our contemporary solar system, we may only then be successful if the bodies are certainly small and have ever been small, so low compression and low heating effects, and if the bodies avoided more or less collisions, but certainly super catastrophic collisions to start with. And the question is, do comets fulfill those criteria? And what would be the inner structure of a comet? And I'll be talking in the second half of my talk exactly about that. So if we sum up the first part, we have a whole series of processes from the formation through the thermal, through the collision evolution to the contemporary planetesimal survivors in the solar system, and ask ourselves, what are their properties? The first is we want them to have a gentle gravitational collapse, so not to destroy the pebbles. That sets the an upper limit for the size on the order of a few 10 kilometers. And if that is the case, then we can relatively easily define the physical properties of those planetesimals. And I'll go through this one by one in the next slides, but here we'll just sum it up. So we expect very low density, meaning packing fraction, because the pebbles are still intact. The pebbles do have void spaces between the grains that make up the pebbles. And between the pebbles, there's also void space. It might be filled with fluffy dust, but it's certainly void space still. We do expect low permittivity, so electrostatic or electrodynamic properties. It should be homogeneous at least on length scales that exceed that of the pebbles. The interpebble space might be filled with other material from the collapse phase. The mechanical and collisional strength of the pebble piles that make up these planetesimals are super low. I'll show you numbers about that in a few minutes. The heat conductivity, as shown before, will be extremely small at low temperatures and will be strongly temperature dependent at high temperatures, which might be a measurable unit. And the gas permeability might also be relatively high due to the large void spaces between the pebbles, which might be an interesting thing for cometary activity. And now we're turning towards Comet 67P as the role model of a comet that has been investigated to unprecedented detail by the Rosetta mission. So Rosetta mission means Rosetta orbiter and Philae lander. And the question is, can we find properties of Comet 67P that match our very simple and maybe even oversimplified understanding of the formation and evolution of planetesimals? And I'll try to answer that question in the next minutes. So we'll start with the packing density. A caveat, we don't know the packing density of Comet 67P. We do know the mass density with a real high precision because we know the volume with high precision and the mass. But the mass density and the packing density, so how much void space is inside the pebbles and between the pebbles, are not the same thing. For turning over the one into the other, you need to know the material mix, and that's unfortunately not really known. So we do have estimates about the dust to ice ratio, and we know ices have a material density of about 1 gram per cubic centimeter. The dust may have a density of between 1 and 3, but this between 1 and 3 is the problem. So is the dust mainly organic with a low mass density, or is it mainly mineralic with a high mass density? That makes a big difference. So there's different estimates. So the filling factor or packing density has been estimated by several groups. So it's just two numbers. So roughly 25% or 25 to 30% is the amount of volume filled with real material. Now, a very simple model of pebbles having a filling factor of 40%, that's a result of a laboratory experiment, and pebble packing having filling factors between 56 and 68% ends up with exactly those numbers. So the estimated observations from Rosetta in our simple estimate match extremely well. That's not a proof, but it's a hint, of course. Homogeneity. The only measurement that has investigated a large volume in terms of homogeneity and in terms of permittivity is the Rosetta Consort experiment, a radar looking from the lander to the orbiter. So the lander was the transmitter, the orbiter was the receiver, and analyzing different paths and inverting from those data the homogeneity and the permittivity. And besides a relatively shallow region close to the surface between 0 and 25 meters, so give or take 10 meters, which has a permittivity that is relatively high, the bulk of the volume seems to be extremely homogeneous down to a length scale of a few meters, which is the wavelength of the radar used. This certainly speaks in favor of a pebble pile and not too much rubble pile with thermal metamorphism. So that is a clear indication for that. But unfortunately, Philae has only worked for a couple of days, and we're stuck with a limited number of available data here. That's something that the JADA instrument on board Rosetta observed. Many particles that were discovered by the light scattering, the light curtain of the JADA instrument, but could not be detected by the impulse sensor. So having not enough momentum to trigger a signal, but being big enough to trigger an optical signal. And people working on that, you're seeing the publications here, mainly in Italy. So have concluded from that a large fraction of the particles with sizes on the order of millimeters to even centimeters, even smaller than that, of course, and potentially even fractals with a small fractal dimension, but certainly with porosities above 99% could have been responsible for that signal. And our model, Marco Fullis, and my model of the gravitational collapse can explain that by taking into account that during the pebble collapse, the interpebble material, which is dusty, sticks to the pebbles during the collapse, and it's just taken along as long as the pebble pile doesn't undergo catastrophic or compressive collisions. So that's is another explanation that cannot be explained by any other formation model, I believe. Strength. Strength is an extremely important measurement at Comet 67P, Churyumov-Gerasimenko. Yuri Skorov and I, back in 2012, so 10 years ago, had already predicted what the tensile strength of a pebble pile would be. And the tensile strength T here is on the order of 1 Pascal if the radius of the pebble is a millimeter, and if the radius is larger than a millimeter, it scales with a power of -2/3. So for a few centimeter pebbles, this tensile strength might be as small as 1/10 of a Pascal, which is extremely important for understanding comet activity. But that's another theme, not for today. But the measurements were basically by the paper of Atri et al. That the tensile strength to the cliff collapse and other things can be estimated to be indeed below 1 Pascal. So you're seeing a histogram here of the measured tensile strength by Atri et al. 2018, and you see the bulk of the data is even below 0.5 Pascal. So that speaks in favor of pebbles being present, first of all, and second, pebbles being larger than millimeters in size. More recently, Larry O'Rourke and colleagues in 2020 measured by analyzing the Philae impact, one of the Philae impacts, so the unsuccessful landing attempts on the cometary surface, measured the compressive strength to less than 12 Pascal. We don't have a model for that yet, so there's nothing to compare with. And the collisional strength is another number, has been modeled by San Sebastian et al. Is also extremely small numbers, orders of magnitude smaller than for the classical model of a makeup of a planetesimal. So that's, again, very strong indications of 67P being a pebble pile. Mentioned before, you've seen that chart from Doro Bischoff et al. 2021 is the heat conductivity as a function of temperature. This prediction faces the observations summarized by Cosset et al. 2019 that the heat conductivity from different instruments combined, there might be deviations at individual instrument level up or down, might be as small or smaller than roughly 10 to -2. So this is the yellow marked region, and you're seeing for 5 millimeter pebbles, this basically fills the temperatures that were present. So again, it's not a proof, but it's completely in agreement with the pebble pile model. And now comes my very earthly cometary analog. I think a planetesimal, or maybe a comet, that is made up of macroscopic pebbles on the order of centimeters or so in size, with a very low packing density, with the homogeneity, the large pore space, the low strengths as shown, and the low heat conductivity can be understood as the ball bath, as you can see here, for children or even adults, if you like. So that's my earthly cometary analog. However, there has been more work on the pebble properties, or the properties of comets that is made up of pebbles. So we studied the pebble sizes back in 2017. We analyzed many instruments, ground-based observations, and theoretical attempts to understand the formation of planetesimals, and ended up at plausible pebble sizes, pebble radii between 3 and 6 millimeters. A recent submission of my group confirms these results with more detailed mirror analyses. However, there's other work by Japanese colleagues who claim from the thermal inertial measurements, also from thermal measurements as we do, claim that the pebbles must be bigger, so bigger than 3 centimeters. You see, there is still there's still room for play here, but it's certain that if the pebbles are present, they are on the order of 1 centimeter or so. And very recently, Marco Fuller and colleagues and Gianniello and colleagues came up with an activity model that's based on a pebble pile makeup of comets. So based on the idea I presented to you, that but it distinguishes our simple pebbles, which are homogeneous internally, by assuming that the pebbles do have inner structure. So starting from the initial grains, we know from many experiments and from simulations that initially when the grains are little, so microns or so in size, or even submicrons, they stick at every collision and they stick without any restructuring. So they grow to fractals. And we do have indications from the JADA and from the METERS instruments on board Rosetta that there might have been fractal agglomerates present in the dust that 67P flew out. As indications of very fluffy dust, as I showed you before. However, once these fractal aggregates become more and more massive, the collision energies increase as well, and then they become more compact. They're still porous, but they become more porous, more compact, and they grow to the millimeter sizes. This is not the end, because pebbles might be centimeter sizes or even decimeter. So these porous agglomerates might then collide amongst each other. I showed you that first movie in the beginning where you could see the experiment, and then form pebbles that have the right size, but do have inner structure. So, and Marco Fuller has modeled that with some distribution of pore spaces. And the elegant thing is, this can describe the activity pattern observed with Rosetta for comet 67P, and basically the activity pattern of all the comets extremely well. So for instance, it's one example, it's not exclusive here. The before unexplained huge increase in activity, that's both for water as well as for CO or CO2 as well as for dust, over strong activity increase as the heliocentric distance decreases, and of course after perihelion the same strong decrease. So one would naively expect that as a body comes closer to the sun and the insolation increases V1 over distance squared, that the activity goes with the same power. But you're seeing here as the distance is linear, but the activity in water in that case is logarithmic. This is certainly more than a 1 over r squared dependency. And this dependency, besides other things, can be readily explained by a pebble model that has substructure. Of course, much more work has to be done, but that's another confirmation that we're on the right tracks with a pebble. So let's sum up. I hope I could show you in the past 40 minutes or so that the nucleus of Comet 67P is, as far as we can tell, homogeneous on all length scales down to about 1 meter, but maybe inhomogeneous below 1 meter. That is a very recent paper by Cianiello et al., who might have discovered water-enriched blocks of typically 1 meter in size or so. That readily needs to be explained. So that's good for the modelers. They have something to do in the future. That comet is certainly highly porous. So with a density of 500 kilograms per cubic meter, nobody doubts that the porosity is high on all length scales down to the 1 meter scale. It does contain ultra-high porosity or even fractal particles, which can only be explained by the pebble collision model unless you form those particles on the cometary surface, and nobody has come up with a model that can do that. It possesses extremely low strengths, so less than a Pascal or so, strengths that nobody had in their books before Rosetta landed. Is macrogranular. I think we could show that a granularity on the order of a centimeter can explain lots of surface properties that we're seeing. Possesses extremely low heat conductivity, again, a result of the pebble pile structure. And on top of that, contains ices that have extremely low melting points, for instance, CO ice, or also CO2 ice, which has low melting points. So that means the body was never really heated throughout the volume in an early stage. So what does that mean for our 5 different makeups of a planetesimal? It certainly rules out the super catastrophic large cometesimal model. So we do have these highly volatile ices. So certainly this model is out of the range. I think the constant measurement rules out a shell structure because different shells at different depths should have been visible unless the abundances of the ices were so low that they never showed up. But we're working on that. I doubt that. So it might also be dismissed. It might rule out to a certain degree the catastrophic collision case with a differentiation, but it cannot rule out those 2 models. In the end, that means that Comet 67P very, very likely never underwent more than a smooth catastrophic collision, which might have rendered it into a pebble pile, but into a rubble pile, but the rubbles are so soft that they probably might have reformed a structure that looks pristine. It was not highly heated, so it was formed small as a small body or formed without radioactive nuclei, nobody knows. And that this model can explain many properties of a comet that we are seeing today and that we have had the pleasure to witness being measured by Rosetta and Philae. So my last slide. This is from a recent review that we published in Universe. You can see the QR code for if you want to have that. It's publicly available. We have a formation stage of pebbles, which might be extremely complex due to the inner structure of the pebbles, followed by possibly a pre-concentration and streaming gravitational instability stage that forms planetesimals, typically with 100 kilometers in size, but these grow typically so fast into planetary-sized objects that only the small ones survive as planetesimals, which is good because the small ones themselves do conserve the pebbles, and the small ones may still contain short-lived radioactive nuclei, but they're not heating up very much because the volume is so small and the length through which the heat needs to be transported is also little. So they might be undifferentiated or might be slightly differentiated and then possibly underwent collisions up to the catastrophic level. So in the end, I think from the 5 different ways a planetesimal can go, Comets only chose either the type A1 here or the type A2 there. And with this, I would like to stop. Thank you for your attention, and I'm ready for many, many questions if you like. Thank you very much.